Hi, everyone. Thank you so much for the invitation and the opportunity to participate in this amazing workshop. So in this presentation, I want to discuss approaches based on group and individual subset scanning and how they can be applied over off-the-shelf deep learning models and different use cases. So first, let me introduce you to the team. The AI science team in the Kenya lab is led by Skylar Spickman, and we also have tight collaborations with the Yorktown IBM Research Lab and Harvard University researchers. Our team is composed by research scientists, PhD students, and machine learning engineers. So let me tell you why we think anomalous pattern detection is interesting for us. Currently in the domain, we can define anomaly detection as searching for an individual example that are anomalous. In these cases, we are looking for a single sample that looks odd to us. That sample is obvious once identified, and we have some prior knowledge of the structure of what we are looking for. We want to expand these ideas to be able to identify a group of samples that look anomalous together. So in this scenario, we will have multiple samples that are affected by the anomalous pattern. And when we look at them individually, these are slightly anomalous, and we have little to no knowledge of the source and structure of the pattern. As we will see later on, searching for a group of samples in the activation domain of neural networks creates a huge search space that we can traverse thanks to previous work on linear time subset scanning. But why we're interested in pattern detections in deep neural networks? As we know, these models are susceptible to adversarial perturbations or other distribution shifts from the input data. And these changes can cause samples to be incorrectly classified. For example, in adversarial attacks, the perturbations contain small variations in the pixel space that cannot be detected by a person, but can change the output of the classifier. So in this presentation, we want to show you how we detect and characterize anomalous patterns in 3 different use cases. First, the adversarial attack example on how we detect them on autoencoders. Then, how are we able to detect synthesized content generated from GANs? This could be partial generation or totally synthesized samples. And lastly, we will see the new class problem. How can we help a neural network to work over a sample that has an unknown class? So when we are using subset scanning, we treat neural networks as generated systems, and we apply anomalous patterns techniques in the activation space. So this means that we are not building different deep neural network models to detect anomalies. Rather, we use it as a source of information. And we think that we have some goodies on this approach. For example, we can provide detection improvements at inference time. We can be agnostic to the domain like images or audio because we are working on internal representation of the data in the neural network. And lastly, we don't have to retrain our models or have extra labeled examples of what the anomaly looks like. So let me first walk quickly over the method that we will see that we will be using across all the different examples. So our main assumption while we are doing our experiments is that activations from adversarial samples or generated samples or from new classes have a different distribution of p-values than clean or quote-unquote normal samples. So for us, a p-value is the proportion of the activations that are drawn from some of the multiple clean samples greater than the activation of the evaluation. But now let's see how can we score one sample at one given node. So for that, we use the scoring functions over the new sample in order to measure how much of these values deviate from uniform. So we know that subset scanning can use parametric scoring functions like Gaussian or Poisson, but the distribution of activations within one layer are highly skewed and sometimes bimodal. So in the deep learning use case, we use non-parametric scan statistics, so we can make minimal assumptions of the underlying distribution of a node of activations across one layer. So this gives us the potential to be able to scan across different type of layers in a given network. So as I mentioned before, subset scanning treats the detection problem as a search for the most anomalous subsets of observation in our data. In our case, the activation space of our deep learning model. So we can efficiently scan over this exponentially large search space and identify the subset that maximizes the divergence of p-values between what we observed and what was expected across all nodes of a layer. So this method will give us two outputs. First, a score of the anomalous pattern, and the second is the subset of nodes that contribute to that score. So in the presentation, you will hear that sometimes we refer as group scanning or individual scanning. So the simplified difference of these two will be our search space. On individual scanning, we will pass one sample over the activation space, and we will scan which group of nodes are the ones flagging that sample as anomalous or not. In group-based scanning, our search space will be which group of samples and which group of nodes actually are the responsibles to flag an input as anomalous. So let's walk over the steps to apply subset scanning methods over already trained deep learning model. So first, we need to extract the activation of the deep neural network train for both background images, what will be our null hypothesis, and the evaluation samples. Evaluation samples could be noise, perturb, or not. After we have the activations for all samples, we can compute the empirical p-values and filter them by alpha threshold. And this will form the distribution of expected activations at each node. This will give us, quote unquote, what normal looks like. So this is done by letting the model process the samples that are known to be clean from anomalies and recording the activation output at each node. After we have all our background images, then we will score the test image. This again could be clean or could be noise, and we will record the activations that are induced by these test samples and compare it with the baseline that we just created on the previous step. So this type of comparison will give us back a p-value at each node. So lastly, we will need to quantify the anomalousness of the resulting p-values, and this will be by finding the subset of nodes that will maximize the non-parametric statistic function that we will define before. So this method will give us two things. Again, it will give us the score of how anomalous the pattern was, and also the group of nodes, or if it's group scanning nodes and samples that were responsible for this score. So now let's see one of the first applications, and is how can we detect and characterize adversarial attacks for both image and audio domain. So just as I mentioned previously, adversarial attacks are very smart perturbations on the input data that will make the model misclassify the sample. So one way that we can classify these attacks is by the threat models. So we have white box and black box attacks. In the white box approach, the attacker will have complete access to the model, including the structure of the network and the trained weights. In the black box approach, the attacker can only access the output of that model or the predicted probabilities. So we will show results in both cases. So previous work in this space has already shown the autoencoder networks can detect these anomalous or adversarial images by thresholding the reconstruction error. Other detection methods may also rely on data augmentation or specialized training techniques that will be asserted before the training time. So in contrast, we want to use our methods to enhance the current detection power of off-the-shelf autoencoders without adding any extra labeled examples, retraining, and so on. So as you can see in this figure, for each layer, we will have a distribution of the anomalous scores for both clean or quote-unquote normal samples and adversarial ones. As you can see on the blue distribution and the orange one, we will hope that as more distance these two are, the better the method to detect the anomalies. So in these experiments, we look at two approaches. First, look at the inner layers of the autoencoder, and then also look at the reconstruction error for looking for anomalous patterns. So we can see here that our highest score rely on the layers of the encoder and decays on our way to the decoder. So we can suspect that this is the autoencoder properties to abstract the information to the LatinX space. So as you can see, we run these across different adversarial attacks, and also we retrain autoencoders with proportions of samples and noise during training. So our detection power is reported in the area of the curve that you can see. And in the right, you can also visualize the score of the most anomalous subsets of the Nodax deviations that are extracted from one of the first COM layers for fashion MNIST. So you can see in blue the distribution of the scores for clean images, and in other colors, the distribution for adversarial attacks that has been successful to that model. Finally, something that we think that is interesting is actually analyzing the reconstruction space, because this gives us information back to a pixel space, and we can actually interpret or see which are the pixels that were modified, or at least the ones that trigger our method to be anomalous, that are the white pixels on the image. Lastly, a quick update on the results that we can see for audio. So usually when we are looking at adversarial attacks in audio, these are predominantly focused on preprocessing techniques. So this means it's going to be some sort of filtering or compression that will modify the input. And they already know that actually reduce the quality of the benign samples. So we can see that with our method, we can achieve similar performance to these preprocessing methods, but without losing the accuracy of the benign samples, as we don't modify the input samples. So in our second application, we are interested to see if we can detect synthesized content by generative models. So we can see that now we have almost near realistic generated content at a high throughput capacity with these generative models. So there are multiple concerns if we were able to detect in the near future if a sample was generated or it was modified from the original sample. So what we wanted to do in these experiments was how can we enhance the performance of each discriminant component of the gangs and also other off-the-shelf fake classifiers to be able to detect these synthesized images. So in our experiments, we use a total generation like Pishigan. This means from a noise vector, we will have a full face generated, or also other methods like star transfer or attribute modification that will only change one part of the image. For when we were working on the discriminant component, we are also researching to see if it's possible to mask different nodes. So when we retrain, we will only retrain a subset of these nodes and speed up the process. But also looking at a more general approach is how can we enhance any fake classifiers we don't depend on the knowledge to know each discriminant of the Gantt, and we can receive different sources. So we were able to achieve a reasonable detection power on both having total synthesis or partial. But we are also interested here in to see till which proportion the model is able to detect correctly. So here we are trying to say what happens in 10% of the samples that I'm receiving and are generated, what happens when it's 20, and so on. We can see that at higher percentage, our model for group scanning is able to detect almost perfectly which are the samples that are being generated. And when we get that percentage low, we lose detection power. So we can see that till 10% of the samples being generated on the batch, we have good results there. And we will see slowing down as we get smaller and smaller percentages. So the last application that I want to discuss is on the space of dermatology. What happens when we train a model with a group of known conditions and we left out other classes? Or also in the other use case is what happens when we have a shift on the clinical setting, like the acquisition devices changing, the illumination, ambience, and so on. So we have some preliminary results that are being presented by Hannah Kim on KDD OOD workshop. And it was interesting to find that over the best performing model, I think, if I remember correctly, was a DenseNet that will classify different conditions. And when we scan over this model, we can see different subset scores for the two different use cases. So for the new class, the unknown class, we see similar patterns on the scores that you can find for the plot on green and yellow. And then when we're looking at the change of device or hardware change setting, we see a total different pattern there. So it's interesting that this could be a proxy for us to give information regarding the source of the anomalous pattern, not only say that something is wrong, but we can actually say that this belongs to a new class problem or belongs to a clinical setting change. Also, in this work, we were interested on the fairness aspect or OOD. And something that we observed was that we had different performance when we are looking to samples from dark skin tones. And this sort of instability of the performance may be partially due to the network that is trained lacks of of samples of dark skin tones and is mainly Caucasian, what we're looking into right now to get more insights on the reasons. So some conclusions from this work is basically think that we are not claiming that we are the best method for each use case, but rather that we can use a general method, abstract of the implementation of the deep learning model, abstract of the data domain, and being able to enhance the power detection of these already really well-tuned deep learning models. And for that, we don't need to know examples of what the anomalies looks like, nor retraining or data augmentation. But we do definitely need data on what normal looks like. So this will give us an agnostic application to having different data and different architectures, and we can sit on top of already trained models. Now we are exploring in more detail the subset of nodes that we have back. Can we use this to detect the type of source? For example, can we detect which type of generative process created a sample of which type of adversarial attacks? We are also interested in looking how can we use these nodes to improve retraining techniques of deep learning models. Furthermore, we are looking on layer selection. As you saw, depending on the problem, some layers will be more useful than others. And that we need to figure it out if we are going to depend on the context that we are running, or it can be an heuristic method to find out. So the code for the adversarial attacks is actually available on the Adversarial Robustness Toolbox, and the paper on each guy is also available. But most of the examples that I show you, you will have an archive version for sure. So I would like to take a few minutes and just highlight other amazing work that we have on the lab. So we are very strong on fairness research and also machine learning in global health. So I would invite you to check out other papers that our research colleagues are working on it. Thank you so much for your time. I hope you find this topic interesting as I do. Now happy to answer your questions. Thank you very much.
Okay, well, thank you so much, Celia. That was a fantastic presentation. And now we're going to open it up for probably about 10, we're a little bit ahead, so maybe 15 minutes of Q&A. So we'll be taking questions from our, both from Zoom and from Rocket Chat. So participants, please feel free to post any of the questions that you may have in either venue, and we'll be sure to try to get to those questions. So to start with, I think I have a couple questions I'd like to ask, and to kind of get the conversation going. I think you mentioned that it's model agnostic, this technique, right? So you can basically apply it to any model, and look at the individual layers of the model as a source for determining the anomalies. And so because of that, it kind of makes me think there's going to be a difference in performance depending on the model. And then there's also going to be a difference in performance on the way that the model's trained. And so, lots of things start coming to mind. So hyperparameter, the effects of hyperparameters on the pre-training. And I'm assuming that you're using pre-training. So could you speak a little bit sort of to those ideas? If you're using pre-training, what data sets, where those models pre-trained on, because that also may make a difference. And maybe thoughts on how sort of to mitigate that.
Yeah, definitely. Thank you. Thank you so much for the invitation. So actually, we always depend on the performance of the models. So we are always assuming, and when possible, use models that are already available on the zoo or from other paper applications. The idea is that we don't want to tune and we don't want to mingle anything in the training process. We think that getting the state-of-the-art performance in a given task should model. But for sure, for the autoencoders example, we see that when the autoencoder is trained poorly and you see that the reconstruction error space is very noisy, we lost a lot of detection power there, of course, because not even the reconstruction error is actually being divergent between those two set of distributions. Will always reconstruct noise. But in the side of why we are agnostic to different layers and different models, I think the core idea is that we use non-parametrics tests, right? We are not assuming any particular distribution and that we are able to run over different structures. But again, our idea is take off-the-shelf models and try to improve in inference time the detection capabilities. So of course, poorly trained models have a poorly representation, right, in the inner layers. So that always goes the way to the increment. So we are assuming that the model is actually performing well. And we usually like to look for latest paper on a given task and then just use the models that they provide.
Great, thank you. So I have some other questions. I don't want to take up all the time. I'm just waiting to see. No other questions? Okay, so I work in sort of the simulation space and the synthetic data space. And so I'm always curious, I guess I might answer my own question, but have you thought about using synthetic data? Perhaps not for training, but for, for inference, because my understanding is that you're not doing any type of fine tuning on the pre-trained models. Is that right?
Yeah, exactly. So basically our models is we only know what quote unquote looks normal in the distribution, what was the data was trained on, that information we need, but we don't have any label data of what the anomaly would look like. On generated models, what we have a work that actually some preliminary results were presented on subset ML workshop here at ICML is around how detecting generated content. And actually we found out that using individual scanning was not sufficient there because the modifications were more subtle. So we actually need for search for group of images and group of nodes in one layer that can give us information if the sample was generated or not. And that's super interesting, right? Because better gangs like PGGAN or style gangs that are acquiring an amazing capability of generating data, it's not sufficient to see what sample and say, okay, this probably is generated or not, but rather we are looking for subtle patterns that they share together, right? The same gang generating these batches of images will give us a trace of how it was generated. But around gang models, that's what we're working on. And we have some lines on actually how to improve gang training process, blocking out the nodes that look anomalous to our method and so on. But it still is super green area. We are heavily experimenting.
Kind of like based on the discrimination score, I guess, whether or not you allow training for that particular node, or kind of like dropout, but sort of selective dropout.
Exactly. That's the point. Like a selective dropout, and just saying, okay, the discriminator felt that that image was weird in this set of nodes, so we can freeze the rest of the nodes and just work a little bit more on those. Yeah.
Gotcha. Fantastic. Let me check. Do you have any other questions? Nothing yet. I'll also see if any of our program chairs or anyone else on our side has any questions. So I also, I guess while we wait there, I also have some interest in sort of bias, and it's interesting that you noticed a change in the way that the performance of the discriminator based on skin tone. So I know that you mentioned briefly kind of what you think that might be due to, but could you sort of maybe conjecture a bit on the sources of those, a little bit deeper on the sources of those forms of bias, and perhaps do you envision your technique being able to help in that respect in terms of improving and sort of closing the loop on the training side? Because I know that you're not really retraining or fine tuning, but perhaps this could be something that could sort of help folks who are trying to produce trained models that don't have that type of bias.
Yeah, that's actually a great question. So we were looking at the fairness angle for that work too, because we have previous work also on analyzing machine learning data sets in dermatology, and also diagnosis classifiers telling you different types of melanoma. And we actually work on stratifying those and actually having performance analysis on skin tones variations. And so from that work, we had like data sets were always heavily skewed on Caucasian population, right? There wasn't any tan or darker skin tones representations. And when we are looking for out of distribution, then the same questions arrives. This is not a classifier that is gonna give me the diagnosis, but actually I wanna see if my own method on detecting outliers will change across different skin tones. And we see that there is way more instability around each layer when we look the anomalous score for darker skin tones. Our heavy assumption for now will be also that data set that we used for training was also heavily skewed to Caucasian populations. So one branch of the work that is on MDScan actually is really interesting work that I think is on the AI 360 Fairness Toolkit, or at least has a pull request already at the public. That what we do is actually search for subgroups that are being misclassified at a higher rate or a lower rate. And I think that work has the same search space that we use for deep neural networks, but we can move it to our other type of classifiers or even just the data sets. Usually when we are looking on bias and fairness, we have protected attributes in our mind, right? We say, okay, we will check for gender, for ethnicity, but with MDSS, this same search methodology, you can actually search in an unsupervised manner, which are these protected attributes. And not only that you should look for gender or ethnicity, but also you should check for this particular gender, these ranges of ages. So is basically in the methodology wise is the same search that we do, just we move it away from deep learning and we use it to other models to get a way to search for which attributes we should be looking for when looking at higher or lower misclassification rates.
Excellent, thank you. So I see that we also have a question here that came up in Rocket Chat, and you may have answered it already, but I'll just to make it, make sure we all we represent everybody's views and questions. So we have a question from Pablo Samuel Castro, and he says, the skin color issues you mentioned at the end seem quite challenging and important. What ideas do you have for tackling this?
Yeah, this is a great question. So maybe we'll skip a little bit the OOD detection part for sure. But we are closely working with dermatologists in another projects on how to measure, right? How we quantify skin tone representation in data sets is already a problem that we're working on. I think the first
step is actually recognizing, detecting this type of bias. So before datasets, I think one paper a few months ago released labeled datasets with an skin tone range, but before we didn't even have that type of information in the dermatology datasets. Something that we were also interested is that when we released the first fairness paper related to skin tone representation, dermatologists approaches to us and say, we have exactly the same issue, but forget about machine learning or our textbooks, papers, things that are being used to train dermatologists also lack a lot of darker skin tone representation. So we even have to step back. I think it's a huge movement that is happening right now. Also dermatologists during COVID, they are trying to collect data to different to check for COVID manifestation rashes, and they are having the same problem. Like most of the registry is Caucasian population. So I wouldn't give you any current solutions. I think right now we're looking at the point of representation issue. I saw some works that trying to use, generative models to try to augment the data set or tweak samples in other ways. But when we discuss with dermatologists, that approach usually is not that easy to share with others. So I think right now it's just detect the type of bias that we can find, like skin tones, be transparent on how the model was trained, the population that was evaluated on, just be explicit. This is the population that we tested. These are worst, best case scenario. But I at the moment, we don't have any augmentation technique to solve this problem.
Great, thank you. Thank you for the fantastic answer. All incredibly important questions that I think, especially for folks from our community, are particularly relevant. So thank you so much. So we have about 1 minute left in this Q&A session. So I'll just I'll see if there's anyone else who would like to ask any further questions. And if not, we can conclude. Doesn't seem like it. So I'm trying to account for any delays across the world. So, okay. Well, I think we can safely say the Q&A session is. Oh, I see somebody's typing. So let me just briefly wait. Maybe we can get one more in. Oh no, it was just a thank you. Okay, great. So I think this concludes our session. I'd like to thank you, Celia, very much for your contributed talk and the Q&A. I think it really covered some amazing ideas and research, and hopefully our community got a lot out of it. And so thank you again.